This video extends the concept of Gaussian quadrature to two-dimensional elements and then concludes with an example with finding the stiffness matrix for a 2D quadrilateral element. When we do 2D integration with a single integration point, that's basically like evaluating first one integral with a single point and then the second integral with a single point. So we just evaluate the two integrals applying the Gaussian quadrature approach. So instead of having a single summation, we're going to have two summations where we sum over the number of intervals in the s direction and then over the number of intervals in the t direction. So for this particular case, if I'm using the standard element for a bilinear quadrilateral, it's going to go from -1 to 1 in each direction. So the width of each interval is going to be 2, and I'm evaluating the function right in the middle of the s and t coordinate system, so where s and t are both equal to 0. That gives me my single point integration for a 2D quadrilateral. This is called reduced integration for a linear or Q4 element. Now, if we want to ramp things up a bit, we can go to 2 integration intervals in each direction, or 2 by 2 integration points. It's going to give us a total of 4 integration points because we have 2 in each direction. This gives us full integration for a linear quadrilateral element, or Q4. In other words, it's going to give us exact stiffness matrix results when we have a good element. It will give us reduced integration, so incomplete results for a quadratic quadrilateral element, or Q8 element. So here's the integral that we're trying to resolve, where the integrand in there is the BdB terms inside the stiffness matrix expression. We're going to approximate this as a double sum of the weights times the function evaluation at 4 total locations, 2 different locations in S and 2 different locations in T. That looks like this, where we have the 1 and the 2 locations for S and T. We plug in the actual numbers where we're evaluating at plus and minus 1 over the square root of 3. And then let's explore this a little bit. This first term corresponds to what we call our first integration point. So we're evaluating the function at -1 over the square root of 3 in the S direction and -1 over the square root of 3 in the T direction. The second term is for the second integration point. We're evaluating in the S direction at a positive 1 over the square root of 3 and in the T direction at a -1 over the square root of 3. Go to the third term here. That corresponds to our third integration point where both the S and T terms are positive, and then lastly the fourth integration point where now the S is negative and the T is positive. So that explores our 4 integration points. Those are the 4 terms that have to be added up together to give us the approximation for an integrand using the 2 by 2 integration points. So if we want to ramp it up one more time, we can do 3 integration points in each direction, or 3 intervals across the total -1 to 1 range for each, the S and the T variable. This 3-point integration in each direction gives us full integration for the quadratic element. So in other words, for a Q8 element that has a good shape, we will get exact results for the stiffness matrix using 3 by 3 integration. Here's the integral that we want to resolve. We're going to break it into 3 widths in the S direction and 3 widths in the T direction, where we're going to evaluate each direction at S and T equal to 0, but also at plus or minus the square root of 0.6, or the square root of 3/5. Let's take a quick look at the first 3 integration points. So at integration point 1, the width in the S and the T direction is 5/9, and we're evaluating at the position of negative square root of 0.6 for S and for T. Moving up, the next integration point, we have a width in the S direction that's still 5/9, but in the T direction, that's our center one that has the wider width, so that's our 8/9 width in the T direction, and then we're evaluating at negative square root of 0.6 in the S direction and 0 in the T direction. And then continuing, the third point, Again, we're back down to 5/9, 5/9, and we're doing it at negative square root of 0.6 in the s direction and positive square root of 0.6 in the t direction. Then we have 3 more terms corresponding to the middle row there, where s is equal to 0 at each term, and then finally for the row on the right, where s is equal to the square root of 3/5, or the square root of 0.6 at each of those. So we get a total of 9 individual integration points for this 3×3 integration. So now that we know how to do Gaussian quadrature in 2D, let's take a look at that stiffness matrix we want to evaluate. So this is in the S and T space at this point. We're going from -1 to 1, so it's a 2×2 square. And we have B transpose, and the Jacobian determinant, all that are defined in terms of S and T. If we are evaluating this for a Q4 element, or a bilinear quadrilateral with 4 nodes, the stiffness matrix can be found by either using full integration. Full integration is going to be evaluating at the 4 points shown. Let's walk through how we evaluate it at the first point. So the width for each of these rectangles is going to be 1 by 1. So 1 in the S and 1 in the T direction. So 1 times 1 times the H that comes from out front. Then we're going to evaluate the transpose of the B matrix at this location 1, so where S and T are both equal to -1 over the square root of 3. Then we're going to have our D matrix, which usually does not depend on position, but it might. And then we'll have another B matrix where we're evaluating the same location. Remember, everything along this line is evaluated at this location, -1 over the square root of 3 and -1 over the square root of 3. Then we evaluate our Jacobian at that location, and we continue with location 2, location 3, and location 4. That would be our approximate solution using full integration for a Q4 element. And if that was a good element, i.e. an element that has a constant Jacobian, then this would be the exact result as well. If the Jacobian is not constant, then this would be an approximate solution. For reduced integration, it's very similar, except now it's a single rectangle with a width of 2 in each direction, so 2 times 2 times h, and then we simply evaluate everything in the middle of the range, so where S and T both equal 0. So let's put this into practice. This is an element that we've looked at before. We found the B matrix for it. What I want to do now is use that B matrix to find the stiffness matrix for it. To use numerical integration, that means we've got to evaluate the integrand at the integration points for this element. For full integration, that's going to be 4 different points, plus and minus 1 over the square root of 3 for both S and T. For reduced integration, we're going to evaluate that integrand at a single location, S and T each equal to 0. For right now, let's take a look at the reduced integration approach. For a bilinear quadrilateral, in other words a Q4 element, the B matrix always looks like this. It's made up of partial derivatives of each of our 4 shape functions with respect to x and y. Now remember, we had to go through the process of finding the Jacobian and then using the chain rule expansions to find the partial derivatives with respect to x and y, because the shape functions are defined in terms of s and t. Now we did that all in a previous video. In that video, we found that the partial derivatives of shape function 1 with respect to x and y are as shown, with respect for shape function 2, for shape function 3, and for shape function 4. In addition, in that process, we also had to find what the determinant of the Jacobian was. So what we want to do is use all of this information from the prior video to find k using, for now, reduced integration. So for reduced integration, we want to evaluate this B matrix and the determinant of the Jacobian where S and T are equal to 1. So we just take our expressions that I just showed you for the partial derivatives, and we evaluate them by setting S and T equal to 1. So in this case, we get that the partial derivative for shape function 1 with respect to x and y are respectively -1/14 and -3/14. So I can now plug those right into my B matrix as shown. And we're going to find that there's a 14 in the bottom of everything, so I'm sticking it out front. For shape function 2, we find the partial derivative with respect to x is 4/14, and with respect to y is -2/14. Again, I can plug that right into my B matrix, evaluating it at s and t equal to 0. For shape function 3, we get 1/14 and 3/14. That goes in there. And for shape function 4, we get -4/14 and 2/14. And those go in there. So that gives me my B matrix evaluated at S and T equal to 0. And the determinant of the Jacobian, that's even easier. That's going to give me 14/8 or 7/4. So now to find K, I have to evaluate B and determinant of Jacobian at 0, 0, which I've just done, and then I multiply them. So I'm going to have the width of each interval, so 2 times 2, the width in the S, the width in the T direction, times H, the thickness of my element, times the B matrix transpose evaluated at 0, 0, times D, times B evaluated at 0, 0, and lastly times the determinant of the Jacobian evaluated at 0, 0. So the first piece, that remains the same. Then the B matrix evaluated at 0, 0 transpose that I just found. Then let's assume plane stress for right now. That's what my D matrix looks like for plane stress. And then I've got my B matrix again, not transpose this time. And finally, I have the determinant of my Jacobian. Let's multiply these terms out. First of all, we'll assume that I have a thickness of 0.1 inch. I've got Young's modulus of 30 times 10 to the 6 psi and a Poisson's ratio of 0.25. Plug those into my plane stress D matrix and then multiply out the terms. I end up with 10 to the 5th over 28 times most of the B transpose times most of the D matrix and then B. Now this is just a matrix multiplication. It's time consuming by hand, but it's pretty straightforward. Multiply that out and we will get K. So this is the stiffness matrix we end up with when we multiply those three. This is the reduced integration stiffness matrix for the Q4 element shown there. I went ahead and followed this process for full integration, so evaluating the integrand at 4 different points, and this is the stiffness matrix that I obtained that way. It is in many ways similar, but if we just grab a little 2x2 section there, we can see something typical. Full integration usually has a higher stiffness, as you can see there. So that means reduced integration effectively is going to soften the structure, and this is a common result that we see. Sometimes it softens it too much, sometimes it softens it just enough to offset the fact that FEA primarily is more stiff than necessary. So sometimes people will use reduced integration in order to deliberately reduce the effect of a too stiff structure. Okay.